Good morning, distinguished guests, esteemed colleagues and valued partners. As Managing Director of FEUGA, it is both an honor and a privilege to stand before you today as we gather in this magnificent venue, the Palacio de La Oliva, in the vibrant city of Vigo, to celebrate the culmination of the European Morpho project. This final conference marks the conclusion of an extraordinary journey, one defined by collaboration, innovation, and a shared commitment to excellence. Established in 1982, FEUGA is a non-profit organization with a mission of bridging the gap between research and industry. FEUGA has been a cornerstone in fostering collaboration among academia, enterprises, and institutions. Our foundation is dedicated to driving technological development and innovation, ensuring that groundbreaking ideas are transformed into tangible solutions that benefit society as a whole. The aeronautical industry holds particular significance for Galicia. Over the years, this region has become an emerging hub for aeronautical innovation, thanks to the efforts of both public and private stakeholders. Galicia's unique geographic position, coupled with strong industrial heritage and robust research ecosystem, has positioned it as a rising star in this critical field. Key initiatives, including those led by organizations such as INTA and the Civil UAVs Initiative, has propelled the region to the forefront of unmanned aerial vehicle development. These efforts have not only reinforced Galicia's role in advancing aviation technology, but have also contributed significantly to Europe's broader goals of sustainability and innovation within the aeronautical sector. The Morpho project itself has been an outstanding example of how collaborative efforts can lead to impactful advancement. By bridging together interdisciplinary expertise from across Europe, this initiative has tackled some of the most pressing challenges facing our industry. The results we celebrate today are a testament to the power of teamwork and shared vision. The outcomes of Morpho extend beyond the aeronautical sector, creating synergy with other key industries in Galicia, such as the automotive and naval sectors. Both of these industry pillars of the Galician economy share a common focus on innovation, precision engineering, and sustainability. The technologies and methodologies developed through Morpho have the potential to enhance manufacturing processes, improve materials, and optimize efficiency across these interconnected sectors, amplifying their competitiveness on a global scale. As we reflect on these achievements, it is impossible to overlook the unique setting of today's event. Vigo, a city of profound historical and cultural significance, also serves as a beacon of innovation. As Galicia's largest urban center and one of Spain's most dynamic industrial hubs, Vigo has long been a leader in sectors such as maritime engineering, fisheries, and increasingly aeronautics and advanced technologies. Its strategic location, coupled with its commitment to sustainability and economic development, make it an ideal host for an event of this magnitude. I would like to extend an invitation to all of you to explore the many wonders of Vigo during your stay, whether it is the breathtaking views of the Ria de Vigo, the rich culinary traditions, or the warm hospitality of its people. Before concluding, let me express our deepest gratitude to all those who made this journey possible, to the researchers, engineers, project managers, and countless others who contributed their time, expertise, and passion. Enjoy the rest of the event and your time in Vigo, and we look forward to welcoming you back soon. Thank you very much.
Thank you very much, Javier. And to continue this event, I have to say that there is no event without not last-minute changes, so our agenda has changed, and the project officer that was supposed to participate right now has moved his presentation to later on. So instead of continuing with this introductory move, we will jump into the technical part. And I will give you our project coordinator, Nazih Mechbal, together with Oscar Almeida from SAFRAN, so to dive into the Morpho project already. So let's go.
Gracias. Muchas gracias. So I am Nazih Mechbal. I am the coordinator of Morpho. I'm very happy to see all these colleagues that comes to attend this last final workshop. So thank you very much for your presence. So we are going to go directly to some technical part, but before exactly the outcomes of Morpho that will be presented by the colleagues, we are going with Oscar, my colleague from SAFRAN Tech, to give you what we imagine can be Morpho, beyond Morpho. So I'm not going to, this is the title, I'm not going to convince you, because I think all together here you are already convinced, but we are going just to give you an insight about what we call the cognitive paradigm of life cycle management. So this presentation will be done in two parts with Oscar. So the first part will be some general challenges and issues links to this theme, and then Oscar will go deeply in some example coming from SAFRAN. Okay, so let's go to skip on the time and have some. It's not me. This is the blade. So sensitive.
So sensitive.
So sensitive. Yeah, because there are beautiful sensors from iPhone. So okay, let's go. So welcome. So beyond Morpho, because Morpho is ending now, and how we can imagine what we can do after. And I see all this beautiful work that is done by the Sisters project. So it's to go through a cognitive paradigm for life cycle management. Here, it's dedicated to aeronautical parts, but can be generalized to all structures. And, it's not me. And typically, all the composite structures. So why? It holds immense potential to go smarter, adaptive, and sustainable. Digital transformation, specifically in aeronautics, is coming, and it's now. So there can be this approach of cognitive LCM provides strategic advantage by enabling system to think, learn, and improve. It takes advantage of extraordinary in sensors. I think it's yours. It's your heart, Angela. High-end computing power, increasing, offer transformative potential for aeronautic, for sustainability and efficiency, safety, and can achieve breakthrough in environmental impact and cost effectiveness. This is linked to this approach. So what is the advantage of that? What is the cognitive paradigm? Is a framework that integrates cognitive process, data-driven, and adaptive learning. It supports the availability of aircraft sensors, data, and simulation. This is what we did in Morpho, what we are doing in lots of projects here, but it's a generalization that we're trying to bridge to the industry. Use advanced tools like AI now, machine learning, that will make the system thinking by itself, continuously improve the management of the process across all the life cycle. So some advantages, safety, it's evident. If you have something that thinks by itself, so we can do some rule estimation online, so we can be proactive, so reduce the risk. Cost efficiency, for example, SAFRAN. Proactive maintenance, so less shutdown of the structures, so lower cost over the aircraft life cycle. Sustainability, of course, improve the recyclability and life cycle feedback, minimize environmental impact, and innovation. With AI, we will accelerate the conception, the development, and improve the reliability. So I'm not going to convince, as I said, because you are convinced about that. So some challenges. Sensor integration is still a challenging issue. We did something here with Morpho, but it still needs more project, more effort from scientists and from also industry to do this link between what we did in, what we're doing in labs and to go to more higher terrain. It's me? Why? Because this is... Okay. So it's still a challenge. And then we have data integration and assimilation. I think we have some colleagues here that work on that. It's really a hotspot to do assimilation, how we can have all this data coming from different sources and how we can mitigate them, fuse them. And because you measure different data coming from different type of sensors, and you have the simulation one, so you have to merge everything. It's really challenging issue scientifically with some different methods to do that. AI is now, we live with AI now. We cannot do something without taking into account all this power that's coming from AI. So prone to rely on machine learning model, which may be prone to inaccuracy if trained insufficiently. So we need data. We need data. We need a lot of data. A prediction of some rare events can require expensive computational efforts. Digital twin complexity. The digital twin, it's something that it's a word that is we all do a like of digital twin, but when the system is completely complex, it's not easy to have a digital twin to take into account all the parameters, all the environment, all and reduce and need really intensive resources. So simulating dynamic loads, material degradation, environmental effects in real time, it's not easy. We don't know to do it now in some really complex structure or environment. Cybersecurity risk, this is coming from the industrial point of view, because if you use wireless communication, IoT, so in some industry, it's not allowed. It's not allowed. We don't imagine SAFRAN with his all doing some communication in some situation. I think it's not allowed. Or you have to.
I think wireless communication is a question of frequency bandwidth. Some are restricted, so
yes.
And it doesn't have to disturb the
others
aircraft communication. That's
and also for some cyber security and risk.
Attacks.
Yes. Okay. Now some operation issues or challenges. We have the implementation cost. So it's needs from aeronautical industry significant investment and infrastructure. It's not something that you can plug and play. It needs really to hardware and software investments. It can be an issue for some smaller companies because you need this financial constraint. They can face this financial constraint and then block the system. You have also the system maintenance and scalability. So cognitive system require ongoing maintenance, update and scalability to handle increasing data volume. You need also to adapt the system to different aircraft, and this is not a generic way. You cannot adapt as you want, even if theoretically we can say we do some approach based on hybrid twin, we can then transfer it to everything, but it's not the case, it's not easy. Interoperability with legacy system. So we say that we can exchange data, but in same case, in some industry, there is some sensitive data, and there is no data exchange. You know,
we say that data are the business.
Yes, not data exchange. So this can make some constraints on this kind of approach. For also issues from certification challenge, which is really a big challenge. We have the IASA with us today, with Elena, so it's something that IASA is working on. It's not easy to certificate for aeronautical parts all these technologies. So adding AI-driven approach, it's more complicated to certificate. So you will have really a challenge to go through this certification AI-driven system. Compliance with international standard, we have this is, I think IAS is working on that with some others, Aerospace Federation, to have some standards. But it's not, we don't have common standards now, until now. So when we will add II, so it will be another problem. And also the responsibility and the who is responsible if there is any problem. And for one of the issues is human. We speak about II, but it's human. It's really the challenges we have to trust in II when it's embedded in the aeronautical part. We have also to skill the gaps, because implementation of management cognitive system specialized. You need more specialized engineering, researcher, and PhD students, stuff like that. It is not the case now. You have to go through this, all this transformation of the skills to take into account all this what's technology that goes around this cognitive approach. And human collaboration between human cognitive system. And the last part is also on environmental and system challenge. I think this is, we are agree with all this that, because you have to do a balance between the efforts of computational that we need to do this hybrid twins, this digital approach, the cognitive approach, and the environmental impacts on it. You know, when we ask ChatGPT, you need a lot of energy. So it's something that we have to be aware. We cannot do what we want without taking in balancing this resource. And the recyclability of materials, we have to think about that from the beginning, from the conception, from the design, to have something that's easy to recycle, to reuse. And at last, ethical and social issues. This is general stuff about IA models, not specific to aeronautic. And the change in job, manual roles, reduced demand for certain manual roles, stuff like that. It's not, it's too tricky to do all this. We are in our lab, we are doing a lot of technology, high stuff, but in reality, if you want to go to industry, you have to take care about all that. So, to overcome, we can think about what we are doing here in Morpho and some projects here to sensorize from the beginning. Really, what we put some sensors inside and on the structure. We have to do it from the beginning. We have to design new structure that integrate new materials. You have new materials that have some properties without adding sensors. You know, you have new material. Lots of work that is done now with some new materials that offer some sensitive sensorization natively that can help doing this paradigm. Data and standardization. Advanced simulation testing. Invest in high fidelization simulation. It's events, and it's not easy also, but incorporate some explained AI to ease the understanding what's coming from this technology, and workflow development, develop specialized training program and upscaling for the staff, and the end, collaboration. What you are doing here. More collaboration between industry, researcher, and I think academia and industry, like I think Oscar is convinced we have to trust. We have to trust us, or this researcher, we have to trust the researcher like Theo, Ludovic. We have to trust the researcher to be prone that to help them, and because we are here to help the industry to get this kind of advanced technology that will help really to go through a new paradigm for life cycle management. So I give the floor to Oscar.
Thanks, Nazih. Just to introduce myself, I'm Oscar D'Almeida. I work for SAFRAN Tech, which is the SAFRAN Corporate Research Center. So to continue on your trust,
Yes.
I'm working for SAFRAN Research Center, we trust a lot academia and research institutes.
We need you to trust
Have
more.
many collaboration. Oh, you want more?
Yes.
Why not? Okay. I will make a short emphasis on the what we call intelligent health and mission management. But first of all, start with what is the aviation market forecast. It has been done earlier 2017 and was based on the forecast for 2036. So what you can see figures here, the increase of deliveries of aircraft by 2036 will be more than 40,000 aircraft. The market value will reach $6 trillion. I don't know if you imagine what it is, but it's a huge market. The traffic growth by almost 5%, and you can notice that the fleet growth also by more than 3%. And of course, COVID happened, and there is a decrease. But what we are seeing today, the traffic is almost back to the 2019 level, even more for the short and medium range flights, upper than what it was in 2019. So it may not happen in 2036, but for 3, 4, 5 years later, but it will happen. So how we prepare? Are we preparing to handle this increase of market, especially for maintenance, repair, and overhaul? We need a ramp up for maintenance for civilian aircraft engines. When we say ramp up, it means more shop visits, more engines per year, of course, have more shop visits, more inspection, more workforces, more plants, more surface, more square meter. And there's a necessity of innovation. That's why I was saying we trust innovation, collaboration with academia. And which is based, or the new trend today is AI. AI everywhere, but you have to build the confidence in AI. You have to demonstrate that you can trust the AI. But detection, spare part detection will be assisted by AI. You can use the geolocalization, knowing where the engine at any time, which is interesting to know the how the environment he has seen during the operation or during many cycles. You even go to automation of photo taking of engine at repair stage. The visual inspection will be assisted by AI, and even the tools will be connected, meaning that when you're using the tool, you can register the feature of any configuration, every configuration, any part of the engines. So it's bring to lots of data. So there's a point I didn't mention here, is the storage of this data, the more space, and this is an environmental concern too,
Yes.
because how to process this data. We're talking about reduction of CO2, but the other way, we're increasing the consumption for digitalization. So it's a balance to do between all of this. So from design to maintenance, there has to be a closed loop between from the design to the MRO part, and you have to get information as you start the operation to give feedback to the design office, what's happened, what are discrepancies or damage, what are the problems you can face mostly or rarely, in order for design office to optimize. So it will be a continuous improvement to get to the optimization of the product. That's why we think that what we call integration of the health management has to be done since the design step. Once we say that, the unified capability of the system is to help to assess the current of the system health and integrate that picture within the framework or the global operational demands. So what are the aim of integrated system health management? Is to enable better management for vehicle and the fleet health. So you have many topics, but it's not new. I think you all know that. It will improve the safety through the use of diagnostic and prognostics. It will help to fix faults when there are an issue, and to give feedback to the production, manufacturing or design. It will help to improve availability to better maintenance scheduling, as you want to move from scheduled maintenance to unscheduled one to reduce the cost, the global owning cost too, which is a big challenge today, because any maintenance, just a figure, when you deposit an engine for maintenance, it's more than $1 million each deposit of engine. So you can imagine if it's happened too often, you are losing money. You have to improve the reliability and also understanding of the current health of the system and the process-based maintenances. We see how we can help to increase this understanding of the system and the current health. And the main and the final point is to reduce the total cost of maintenance, because any unnecessary maintenance is decreasing your benefit. The story of SHM. Do you know that SHM concept is older than all of you in this room, I think? I'm not taking any risk. 1960. And as an old person, if you want to keep alive and continue moving, you have to adapt to the new concept, to the new environment. And this concept has been moving since 1960 to this nowadays, and that's why we're coming to intelligent health and mission management. So I just took the definition of what it is. But the next evolution of the integrated system SHM concept, intelligent health and mission management, delves deeper into utilization of online system, health prediction to modify mission profile to ensure safety and reliability, as well as efficiency through predictive integrity. I think everything is said here. It's very generic, but you can choose what you want in this. If you want to improve the efficiency, to the integrity, the reliability, and it showed that what we have done in Morpho project are the basic of achieving this intelligent health and mission management. So from MRO to the MRO to support maintenance and services, it will ensure and maintain operational excellence for our customer, as we're increasing the capacity for maintenances to develop efficient means for assistance, as I was saying, the inspection, troubleshooting, to provide more efficient maintenance operation, the time around the test reduction, because when you stop, you spend time to check if there is no damage So this can take more time, and having this integrated system, you just have to come and plug and interrogate the system. You know the state, F state. It's reduce the time, and it will help to decide, to make decision, the relevant decision. So then we bring the maintenance requirement to design level for new equipment and system. As we see on the Morpho project, our technology need to be embedded or to be integrated since the design. So for existing engine or already in operation, it will be difficult to change. But for the new development, it's the opportunity to be taken into account and brought to the manufacturer and operation. So we learn from experience in operation. We include support and maintenance system requirements at the design level. Then we can support equipment and system performance in operation. It will maintain or increase same level of performance to reduce environmental footprint of maintenance operation, which is a critical point. And also increase maintenance and associated service revenue and margin. We can develop new service offers. As we were saying, data is the business. So having data, knowing what are the features, the main trend of this, this data can give you, you can think about new opportunity of services, and you can develop. Then you can improve also competitiveness of the maintenance and shop repair. Then you can improve the spare forecast and the spare scheduling to help at shop repair. And the main leverage for that is based on digital transformation. We all know that the collaboration between computational entities and the surrounding sensors technology, we generate data in real time, and real time is one of the base to be competitive, more competitive. Is it time? No. But, so, why not digital twin? It will be a beneficial tool for the industry. The main criteria for digital twin, you have many definitions of digital twin, yeah. But this one I took from what we call Alliance Industrie du Futur, it's the French organization of all in the industry using AI. So it's an organized ensemble of digital models representing a real-world entity which address specific problematic and uses. And the second part, it has to be updated regarding the real entity at a frequency and accuracy adapt to its problematics and uses. But at the end, oh, there's a mistake, a mix of French and English, sorry. I have to take off the S. The digital twin is provided with advanced exploitation tools which allow to understand, analyze, predict, and optimize. That's where we come to cognitive part. You have to understand what's happening, to analyze, and it help you to predict and optimize. So, digital twin is not a goal. It's just a mean to get more benefits in any part of the industry. It's a mean to get benefits. If we come to the just a short representation of what it could help in, you start with the design and virtual commissioning. So you can, Nazih was talking about the simulation of testing. Yeah. You can even simulate how you commission your system. You can optimize the flight time manage and optimize the flight time. You schedule the maintenance. You improve the operator training. It's help in disassembly. We in Morpho project we are disassembling and recycling. And one of the other parts is the supply chain and stock management also, because any problem of parts, if you don't know it in advance, it can block your product life for a longer time. So, embedded lifecycle management with a smart multi-material structure is one of the ways for the industry of future, for the future of the industry, and also for the future of market, aviation market. And as I said before, engineering, manufacturing, and services has to work closely in a closed loop and a short loop, from sustainable design to recycling, and also to help for sustainable aviation market. Thanks.
Thank you. Questions,
Any questions?
remarks before diving into the Morpho? Yes, Mr. Nikos.
Nazih, I have a question for you. I saw that you were referring to explicable AI.
Yes, this is.
What's that?
You have some tools and work and theory to try to explain what you have as results from AI, to not be a black box. There's a lot of work on that. To try to give some way to understand what is behind the result that is coming from AI. It's really, lots of people are working on that.
If I can add something, yeah.
Yes.
AI is data, but you have to relate it to physics to understand what the physics behind this data. It's not only giving figures and trends, you have to relate it to what we call inferences, physics inferences in the data analysis.
As a user or as a developer?
Both.
But also as a user?
Yeah. Because if you give a trend, if you have no explanation, we won't buy it. We won't buy it. Because we need to know what's behind this.
That's why it's called artificial. So it's something that you
Yes, but
suppose that you don't understand.
no, you can understand.
Or you cannot understand.
You cannot understand. That's the first I'd say assertion, but it's important for us to understand. If not, you don't master what you are doing. If you come with say, this happened with that's what data are showing, how you correct that if you don't understand the physics? It's very difficult.
Elena?
Also, it's important for certification.
Yes, this is the this is the point. So EASA speaks. So.
It's actually the transparency behind the
Yes,
decision of an
of
AI
course.
system.
This is the issue.
This is glass boxes, we say, or it's a black box.
Mm.
If we understand how the AI system reached the decision, this is what Oscar is saying. So that means that EASA should certify the AI that you are using.
We hope. We hope. Yes, she understands.
There is in Europe there is what we call AI Act, which will be declined by EASA for aeronautics, and you have to prove the confidence you have in AI results for the certification.
Okay, we are in time. More comments, questions? So okay, so we are going to stick on the schedule. And first, because I want to thank FEUGA and Angela and all their team. I didn't do it in the beginning for all the organization of this day, these 2 days. So we can say good thanks to Angela and FEUGA. And now we are going to dive in some outcomes of Morpho project, and the first speakers are Nikos, who asked the question, and Eric. So Nikos from Synthesites, which is a beautiful company that is working on some specific sensors. And what will be presented is some new on the LTM process, how they developed a hybrid twin with some specific sensors to bring really interaction between the real system, LTM process, and its virtual digital twin and the communication lively on it. Okay, so thank you, Eric. Thank you, Nikos. Try. Yes.
Can you hear me? No?
Let me check. It's not much. It's open. Let's talk again.
Can you hear me? 1, 2, 3. No?
No.
No?
Perhaps I can shout.
I prefer you don't.
You need the second
Okay.
one.
Let me check.
Today, okay, now it's better. For
Now it's loud.
for the presentation of the results we had from the Morpho project. Actually, the concept of Morpho is quite common. We are developing monitoring tools, simulation tools, and we try to combine all them in a hybrid twin, digital twin, virtual twin, and different twins. So our part in Morpho was to develop sensors and monitoring systems for the manufacturing process, which in Morpho was RTM. High pressure RTM for aerospace application. The end user and the main industrial partner in Morpho, as you know, it was SAFRAN, and we have worked with SAFRAN Composites. It's a specific corporate research center from SAFRAN in order to develop the manufacturing processes for their products. I think it's your slides. Yes.
So good morning. So first we will recall what is a resin transfer molding, because we will speak about this, and in Morpho we focus on this process. So as you can see here, we took a 3D woven preform that we put in a mold. We integrate to it some sensors. Here is a fiber optical fiber. Then we close the mold and we compress the preform and we inject some resin. And at the end, after cooling, we can demold and get the final parts. In this process, 3 physics are involved, and our virtual twin numerical simulation will integrate these 3 physics, so flow in porous medium, chemical reaction for the curing stage, and of course heat transfer. So we develop a multi-physics virtual twin of this, so which take into account the pre-heating stage of the mold and the cavity. Then injection, the filling of the cavity with the resin. After that, we have the curing and cooling stage. And of course, we also take into account demolding. Here, be careful sorry. We amplify the deformation shape. So one simulation like that lasts around 5 hours. So we can't use this simulation to monitor in real time the experiment, the process. So we have to build a reduced model to be able to perform this simulation in real time. So here is an example of what we have done for predicting the filling time of the cavity. So we take into account 3 parameters: the permeability of the preform and also the inlet pressure. We perform a design of experiments based on these 2 parameters. We took 3 values of each parameters, and after all those simulations was carried out offline, we build a reduced model based on sparse proper general decomposition with 27 offline simulation, and we validate it with 23 offline simulation, and the error is less, the mean square error is less 1%. Of course, as the data were too small, the amount of data is too small, we use cross-validation algorithm. So, and here you have a movie of our reduced model, and just moving the sliders here, you can get the filling time of the cavity for 1 million combinations nearly instantaneously. So I will say in milliseconds, so it's enough to simulate the process in real time. However, if we compare our simulation with an experiment, we can get a huge error, as you can see here. This huge error is due to maybe in our simulation some material properties are not well known, because we don't know the permeability, for example, of the preform. We don't know the compression load of the mold, and so on. Maybe some physics are not involved in our model, and we can't update the model online during the process. So one way to improve our simulation is to get experimental data in real time. And that's why we propose in Morpho project to include some sensors, and Nikos will speak about these sensors.
Thank you, Eric. So I will show you only our part, synthesized part, which are mainly the electric sensors. But besides the electric sensors, we had also used optical fibers inside the cavity to monitor the process, and afterwards using these optical fibers to monitor the structural performance. So from our side, actually our technology has been developed from the beginning to be non-intrusive at all. So there's no, we only touch the part from the mold, so there are not any sensors or anything remaining in the part from our sensors. And working closely together with SAFRAN Composites, they had developed a tool from scratch, especially for Morpho. It's a let's say simplified geometry of an FOD panel,
And we were asked, based on some first simulations of the flow, we, together with SAFRAN Composites, we found the locations that our sensors should have been installed, because this should be included during the manufacturing of the tooling. And you can see the locations of the sensors here. It was just one on the lower tool. You can see the monitoring units, the Cure simulator, and let's say the computer that was supervising all the system. Specifically for Morpho, we develop two kind of sensors that can be in direct contact with carbon fiber, because normally the electric sensors, because they have a problem with the presence of carbon fiber, you cannot use them in direct contact with carbon fiber. So we develop two kind of sensors, one for the curing and one just for resin arrival, that can be in direct contact with carbon fiber. And that's what we tried in the first time in Morpho, and we had very, very good results. So the preform was placed directly in the cavity. It was compressed, high compression, clamping, and we hadn't seen any issues with our sensors. Our sensors, the Cure sensors, are measuring electrical resistance and temperature of the resin. And as you can see, the electrical resistance is very well correlated to the viscosity of the resin. So in fact, you have a sensor inside the mold that can tell the operator or the manufacturer what is the in real time the viscosity of the resin. So you can see what's happening actually in the resin, in the mold, and you can choose to change your Cure cycle in order to take advantage of some issues that may come up. We have also calibrate the sensors to provide the glass transition temperature in real time during the manufacturing again. And that was also very helpful for the manufacturer to see again the curing and the end of cure, so they can demold, they can open the mold faster and sooner. During the Morpho project, I think we did something like 10 injections, 11, I don't know, 12. So, actually there were also some changes during the different injections with the optical fibers. So you can see that during these injections, the flow patterns were quite different. I don't think that we had even one real bad part, but for sure there were some changes in the flow pattern which we have managed to see with the sensors. Actually, these were the first injections, and these were the final injections, the last three. Also, we changed the Cure cycle in order to optimize the Cure cycle. We thought about changing different parameters of the injection, but the final, let's say, trial of the system in order to validate the performance and the improvement was to inject at high temperature, so to inject at the curing temperature, so there is no special step in the beginning to inject and then to heat up for curing. It was just the temperature was from the beginning 180, injection and curing. So in this case, SAFRAN managed to decrease quite a lot the curing time and the cycle time of the production of the FOD panel. So you can see, just to compare, these are the the last one and the previous one. And you can see the temperature in the previous one. You had a step here at 160 and then heat up for curing. And the last one we just inject and cure at 180. So you can see the development of TG in the different cases. So you can see that there was at least half an hour improvement in the curing time.
Thank you. So now we integrate some sensors and we know how they work. We can use them to improve our virtual twin. This is what we call an hybrid twin. The hybrid twin is a combination of our numerical simulation based on physics plus data coming from the experiment. And this hybrid twin is used to update in real time our finite element model to find the best material parameters that fit the real process. Of course, we can use it also to optimize the process and to, for example, in the curing stage, and also to control the process if we have actuators. So here I will focus, I will recall that in Morpho project we have several kind of sensors, so resin arrival sensors developed by Synthesites and presented by Nikos. But we have also strain sensors, which are optical fibers, and temperature sensors and cure sensors. Here is location of those sensors. The stars are for Synthesis sensors, so 3 lines, and the orange lines are the fiber optics, also the blue ones. So the mold with the cavities for sensors for coming from Synthesis, and here you have an example of the fiber optic integrate to the preform. But maybe next presentation they will show you it more. So with those, we develop an interface that are able to collect the data in real time from the 3 different hardware. So from the injector itself, from Synthesis sensors, and from Physense. They all use different protocol at a different sampling rate. This interface must be able to use the virtual twin and to find the material parameters, to estimate the flow front position, and of course to display some relevant feature of ongoing process. So here is the graphical interface that we develop with all the data in it, and to be able to run it in real time during the process, we use parallel computing with 7 processes. With this, we can correct our model, but to correct this model, we need to build what we call an ignorance model. So even with the real data and with optimizing the material parameters of our virtual twin, some errors remains, and to close the gap between our prediction and the real, we train this ignorance model. So we learn from the first injections this ignorance model. Here we use once again the sparse proper general decomposition, but we can use also machine learning. Yeah? And with this ignorance model, we can well approximate, predict the flow front position during the experiment. So if we have one thing to keep in mind, that the hybrid twin is just a virtual twin, a numerical twin, an optimized virtual twin in real time plus this in-house model. But to build this, you need some previous experiments, some data from previous experiment, of course. So we also we can use now this update or optimize finite element to try to determine material parameters in real time. So here is an example of estimating the permeability on each zone of the preform. So we develop an optimization algorithm, and here you can see that in real time we can estimate the permeability of the different zone based on the data provided by Nikos sensors. However, we could not develop the control part because we have no actuators in the mold. We can't modify the filling during the process. This is the end, so maybe Nikos for
For conclusions,
the conclusions.
it's mine.
Yes.
So as I mentioned before, the new CF sensors, the carbon fiber sensors as we call them, arrival sensors have been applied successfully for RTM manufacturing, quite challenging RTM manufacturing, I would say. A lot of carbon fiber, a lot of compression. The use of the new CF cure sensors and calibration methods can lead to significant reduction of cycle time. I'm not sure how EASA can deal with that, but this is something that, of course, we need to work together with the OEMs and the tier 1 manufacturers in order to see how we can help them. The introduction of the Q simulator can considerably facilitate the implementation of this technology, we have also validated its use together with SAFRAN. And hybrid twins allows real-time prediction of flow front position and local material parameters identification and potentially control of the process. Next step.
Thank you.
Thank you very much.
Thank you. Thank you, Nikos. Thank you, Eric. Is there any
Yes.
comments, questions? Yes, yes, please.
Thank you for the information. Just to ask, for the process monitoring, you use only the carbon fiber from synthesis, or you also use the signals from the LPG?
So what we present here, we only use data from synthesis sensors because for all panels, fiber optics are not present in all fibers, all panels. Sorry. So as we wanted to develop it for all, we only base our between on synthesis. But as you will see in the next presentation, we can also use optical fiber to predict the resin arrival time. But it was not done here.
I think the
No, not in the next presentation.
The next
Then, yeah.
I think the problem was that all the post-processing of the data, the recorded data for the optical fibers was done afterwards. So there was no, let's say, online software that can provide online information to the virtual twin.
Comments, remarks?
Thanks for the presentation. I have a question concerning the optimization we're talking about of the time of the cycle that you managed to reduce. But I mean, if you inject at a very high temperature, I guess the viscosity goes higher.
Faster,
So
yes.
it depends on the size of your part. You can do this.
Sure, yeah.
Do you plan on, or have you, let's say, optimized regarding different geometries eventually? Do you take that into account, or how would you include that, let's say, in the design?
I think it's an information that in the project we prove that it works. So you have the tool, and depending on the specific conditions, specifications of your part, you can integrate it in some way. What we have also shown is that with the Cure simulator, you can do everything without modifying the mold a lot, which is also very important, especially for production. We are working now with OEMs and wind blades, or that they are using this information in real time to control the process, which is very important in their production. So why not using this also in aerospace? I mean, EASA is there, but yeah. But for sure, it can help you to optimize the process. You know, then you can have a static process, but you can optimize it as much as possible before. And of course, you can monitor. I mean, monitoring, it's always good.
Question? Just a remark. In the Morpho project, we want to go into the feedback loop control on the fly, but with SAFRAN, there has some issue with the inject of the pressure, and we cannot do it. They need to add some instrumental stuff to do it. That's why we didn't do it. But I think that SAFRAN is interesting, but the work that's been done from the dedicated sensors from Synthesites and the hybrid twin, which is a tool now, it's ready. It's plug and play. Something that can help them if they want to optimize online in the flight all the injection process. Okay, thank you.
Thank you.
We go to sensor new technology of sensorization based on printing physicity. So will be presented by Ingo from IFAN and Marc Rebier from R&D. The floor is yours.
Yeah, thank you very much. Yeah, now we will focus on the composite part itself, coming from the RTM mold process, which was shown before. But now we will have the part equipped with. Yeah, okay, perfect. Yeah. So here you see the part with printed sensors, and we can use this the sensors for detecting stresses, to detecting impact of the part itself. And so it is important to get some information from the part if we have during operation, for example during a flight, and when you have an impact, bird strike, for example, and you can detect it. And to get some information, we print sensors on the part itself, which you can see here. And these sensors consists of 3 layers. We have a bottom electrode and a top electrode, and in between we have piezoelectric material. Yeah? And this piezoelectric material is able to detect this impacts on the part. Yeah? And how we generate these sensors, we use screen printing process. This is a very fast printing process. So we, as you can see here, we have fluting and printing. So we have a paste with the piezoelectric material, and its mesh is fluting, and then it is printed by the squeaky here, and you have a printed structure then on the part. Here you see the process itself, and it is very fast. You can see it here. It is the fluting and now the printing process, and now the sensor is on the part. So it is relatively fast. And doing this, we produce all these sensors on the surface of the part. Yeah. After printing, we need a polarization process because the piezoelectric materials are unorientated in the sensor, and then to get an orientation of the dipoles, we generate an electromagnetic field by applying a voltage of 350 volts and having a temperature of 100 degrees for half an hour. And then all these piezo electric dipoles will orientate in the sensor. Yeah, and after this, the sensors are able to detect local impacts when we have some impacts on the part. The signal can be detected, and it can be calculated where the signal comes from, and how this works. Mark will give some more information.
Okay, thank you, Ingo. Thank you, everybody, for being here. So, okay. So the idea now that we have a new kind of sensor technology is to make use of it to perform structural health monitoring. So Oscar started defining it, but the idea is to follow damage severity evolution along with time, and just to be able to say, now, when we are in the orange zone, we need to perform maintenance. If we do it earlier, it will cost money for nothing, and if we do it too late, well, it will be too late. So when we speak about structural health monitoring, we have several steps to follow. So first, detection, to know if there is a damage in the structure or not. Then localization, where is the damage? And finally, quantification, how large is it? And these are the various steps we would like to achieve using the printed piezoelectric sensor technology. What can we expect from that? So we have several signal processing steps that we can achieve using piezoelectric sensors. At first, we can measure their electromechanical impedance. It's just the ratio of the voltage over the current at various frequencies. This is just an electrical measurement, but it allows to know if the sensor itself is healthy. Okay, so this is the first step. We can just check that the sensor is working fine. Then, as said by Ingo, and as you will see in the demonstrator, we can record impacts and know if there is an impact, where it has been impacted, and what is the associated energy. We can also do acoustic emission, which is a passive recording of damage evolution. Imagine during loading, there is a crack forming inside, and then the crack, when it propagates, it will generate small noise that can be also recorded by piezoelectric elements. And finally, we can use guided waves or lamp waves, which are guided waves propagating within the structure, and you can interrogate the material itself. So you send wave, and if there is damage in the material, you will have a reflection of these waves by the damage, and then you will be able to collect information regarding the damage. So here, I will just highlight impact measurements and wave interrogation, but within the scope of the project, we addresses the 4 technologies. What is very interesting here is that with one single sensor, you have access directly to the 4 underlying technology and also to the 4 functionalities. So one sensor, but many possibilities offered by it. So for impact event detection, we made a live demonstrator here that you will be able to test. You have a little hammer, you just knock it. It will tell you where you knocked and how heavy you knock. On the interface, you will see the signals that are measured live by the piezoelectric sensors. So 5 are currently active. You will see where you knock, and you will see the impact that you can do. So here you can see that the technology is actually working in real time, and you can get precise and efficient measurement. So this is just for impact events detection. Then to validate guided waves, we used an experimental setup at TU Delft where you can hardly see, but here you have the FOD panel in horizontal, which is in a MTS machine and fatigue under cycling load until it breaks. And meanwhile, you have interrogation by the various sensing technologies available within the project. So data acquisition system for PZT, a camera, and an interrogator for FBGs. So here I will only focus on the PZT signals, but later Theo will explain you what we can do with FBGs. So what we did is just we sent regularly guided waves using regular piezo in the structures. And then these guided waves, when they are interacting with fatigue damage, they will generate an additional echo, and we are able to record it. And from a baseline recording and a recording in a damage case, we were able to isolate the damage signal and then to conclude regarding the presence of a damage. But before that, we checked that we can also actuate lamp waves using printed piezo. So here you have pictures. So we made measurement with a laser vibrometer around the printed piezo when we provide a voltage to it. And you can see that in that frequency range, with the printed piezoelectric element, we are able to actuate and to send a lamp wave. So this is one good opportunity. And for the damage monitoring procedure, so we use the piezoelectric elements. We put that in a probabilistic framework, meaning that we made many measurements in a healthy state. From the measurement, we compute a damage index. Here is just the energy within the envelope of the difference between two signals. And then we made measurement also after an impact has been applied on the panel. So it's an impact using a drop tower, an impact with damaging the panel. And you can see that the damage index computed using printed, so using a subset of the piezoelectric elements, we are able to estimate the damage location, which is here, and to compare it to the actual location. So you can see that we have a small error, but quite reasonable given the complexity of the structure at hand. So we can actively detect damage, here an impact damage, and also localize it using the printed piezo. So in order to summarize, we think that and for us, it's important to keep on working on that because we have many functionalities to exploit. So Ingo,
Yes.
if you want to add some...
Correct. I think we should give a demonstration.
Okay.
So as Mark mentioned, you can use the hammer here and you get a signal here, and it's localized here, as he described. You can test it later for yourself.
Yes, thank you for your attention.
Yeah, thank you for your attention. Feel free to ask questions.
Any questions, remarks?
Yes. So very interesting this technology. But what about the scalability? It's quite a small panel, but I suppose that it aims at the bigger structures. And
Yes, it's scalable. So the printing process is relatively flexible. Smaller structures. Yeah, and we are flexible regarding the sensor itself. Of a robotic arm goes on different areas on a larger part. This is also possible.
Oskar? Yes.
Question: did you quantify the precision on the localization?
For the moment, we have made only preliminary tests. So, we can perform damage localization only on impact damage because they are localized on the panels themselves. So we have, it's like 2 or 3 centimeters on that example. We need to perform additional stuff. But the problem with the fatigue damage is that it's not single point damage. It's diffused within all the panels. So we cannot really localize it. It's not meaningful. So, but it's some centimeters, something like that, on the FOD panel here.
But the idea is to, when it's in services, it's to localize, to detect the beginning of the damage, so the premise. And then you can detect that something, small cracks began. Yes. And then you can look if they can grow or not. And just to, I love this technology. It's not because Ingo became a friend, but what it's interesting because here we use the wires, but wires can be printed too. So then it's easy to industrialize. Now we use wires because, wires they're here because we are in the lab test and we are playing with, but we test in the beginning to print on the wire, so you can imagine that we don't need to have some wireless, because then the wire is printed, it's automatically printed, so you can go at the end and plug, and perform all the measurements and all that
Yes.
stuff.
Yeah.
And one evident advantage is that we didn't mention is that it's very lightweight. It's
Yes.
like 100 microns of
Yes, yeah.
thickness.
Thickness is about 100
so
microns.
you add really negligible weight
Yes.
to the structure.
And
Yeah.
it's really a new paradigm because if one of the sensors don't work, you can print many as you want.
Yes, the printers should be protected. Yeah, so here we print on the surface, and it's not covered. So think about it that it will be. The next thing is to integrate it. This is also what we think about this. Yes.
Is there a way to know if it's working properly, the sensors?
Yes, we can beforehand
The
measure
impedance,
their electromechanical impedance.
Yes.
You just on one sensor you measure the voltage and the current, and this tells you if the sensor is broken, or if it has been depolarized, or if it's being debonded. So you can check before. Yes, because one of the issues is that if the sensors themselves are broken, you cannot monitor anything.
This is the first test that you have to make before going to measurement. And with the impedance, it's very easy. It's very confident to know if something is wrong or not.
And
Yes.
Mhm.
Before going in the step of detection and monitoring.
And specifically with the printed sensors, it was quite tricky because Ingo requires a very flat and smooth surface in order to print the sensors. Because if you have some roughness, then during the polarization process, you can just burn the sensors. And so
You can see it on one sensor. We have here there's a defect where it is burned. This is one sensor here in the front. You can
so
see it,
unfortunately, at the beginning, we were struggling with which one are working, which one are not working. So we developed really that aspect because it's very important.
What is that? Yes.
If an impact happens to one of the sensor wire, is it can be repaired with removing the parts?
Removing, so I think it's easy to remove.
In this case, it's relatively easy to remove because we have a layer in between, an isolating layer. This is a green coating, which you can see here, and this can be removed, and then you can print the sensors again. When the sensors are integrated already, then of course so you cannot remove them, but then they are more protected. So you have. Yeah.
And that's why these technologies have this advantage. You can print more sensors than you need because you don't add any weight. And if you print the wires, then if one doesn't work or the impact has destroyed one, you can use the others. And this should be demonstrated before measurement for SAFRAN. They need to know that you can have any strategy if one or two sensors are not working, how you can always... Yes.
I never tested it, but we can just unplug one sensor and try to see if still the system is working. So.
And that's the reason why we print five sensors in a row at each position, because for detecting of an impact, we only need 3 sensors to calculate the signal time. But when we have more sensors, then we get a more redundant signal.
Yes, no? Last question.
Do you have any estimation of how long the sensor can last? How many years we can use the sensor?
Well,
about 35 years of the blade.
In the case of blade.
So do you have any idea?
Durability, I think it's at the beginning of
it is. Yeah, to be honest, it is at the beginning. We have not tested it yet.
Our main question was it working?
Yeah.
So the answer is yes, and now, as suggested by
And
Ludovic
I
and you, we can envisage the future.
I
So
think
join for future projects.
that the application wasn't the easy one to test that, because with this composite and the shape wasn't the easier easy application to test that. But this is the work that should be done. Durability, estimation, yes.
We are very much interested on this technology if can able to stay for long because of, we have a 20-year warranty for the blade.
The blade, yes. Yes.
Yes. Yeah.
I think that some durability
Yeah.
assessment should be done.
For sure.
For
Yes.
sure, for
Yeah.
sure.
Okay. Last question. Okay.
Have you estimated the minimum ratio between the monitor area and the number of sensors needed?
For the moment, no. If you look to impact detection, we put only 5 active sensors, and it's like, I don't know, 30 centimeter by 50 centimeter.
Yeah.
I think we can decrease. And I've seen example in the literature where you have only 1 sensor and you can still locate the damage.
Yes.
So
You have some algorithms that can be done, but here it depends on the attenuation and of this
exactly.
Mhm.
And
composite
as
that is,
suggested by Oscar, we choose to have some redundancy in case you have failure of sensors. But usually, well, you don't need much. But it depends also on the material itself, yes.
Okay, thank you. Let's thank Ingo and Mark. A question? Yes? No. We have time.
Okay.
My question is related with in-service. Is there any limit regarding temperature for the electric that can be the certificate for
Okay, so the temperature should not be exceed too high, because then it is maybe depolarization of maybe occur. So
the order of magnitude is 150 or
150,
200,
yeah,
something
more
like
than
that.
150 is.
So you cannot put it closer to the motor, for example, but
Yeah.
still you can.
The entrance of the engine and of the fan blade is not above 1.1.
It's
Yeah,
okay.
in this case, but if you want to apply for
Yeah.
another
Okay.
technologies, yes. It's like
Mhm.
ceramic. Ceramic,
Yeah.
so you
But
cannot go up.
This technology is more generable than fan blades. You can apply it on
Yeah.
any structure.
This was only the example, no, for the fan blades. Yeah.
It's not
Yeah.
the easier one, but.
Yeah.
Thank you.
Okay,
Thank
yeah.
you.
Thank
Okay.
you very much.
Thank you very much.
Ingo.
Thank you, Mark.
So now the next speaker is coming from Patras. Some pleasure to introduce Theo from University of Patras, professor, and he will talk about now what we can do with these measurements for rule estimation using some new approaches, mixing some understanding of what's happening inside and some AI neural network machine learning. Okay, the floor is yours.
Am I hear me? Is this working?
Try again.
Okay, can you hear me?
No, I think.
Do without.
Yeah, but it's because it's
So, good morning,
it's
everyone.
recording.
Really thank you that you are here today to see what we have achieved in this fascinating project the last 4 years. So I take a good pass from all the previous colleagues, and we kind of go to the last part of the project, where we wanted to see what we can do with the plethora, a bunch of SHM data from these nice sensors to the direction of diagnostics and prognostics of the structure. Please let me remind you that the project has as a final goal the sensorization of blades. The application is engine blades, although we work in an FOD panel as advised initially, as SAFRAN themselves actually do their tests. So very early from when we were designing this project, our colleagues from SAFRAN put us a couple of challenges. So in terms of diagnostics, although my previous colleague Mark and Ingo nicely show some diagnostic results regarding the impact detection and localization, an equally important feature is the stiffness reduction. A very important feature for SAFRAN, for the end user, is to know how much is the stiffness reduced in a possible blade. And even more, let's say ambitiously, if we can estimate the remaining useful life, which is the prognostic aspect, the prognostic task. And together with my very good PhD student Yanis, and
a couple of more students. We've been working in this stuff the last years. This is not, I don't know. Okay, yeah, it's working. So let me again walk you through the test campaign. A very elaborate and a very unique test setup was set up in TU Delft in the laboratory of my colleague Dimitrios Zarouchas and a couple of very good postdocs that unfortunately are not here today. A lot of people are behind these tests, and I have the pleasure to be on the end and presenting you some results. So a very elaborate 4-point bending test in these FOD panels was set up. And the idea is to have most of the panels initially impacted and somehow test it to see damage propagating. We wanted to propagate damage through our tests. And although fatigue is the very first thing that came up to our mind, this would lead to multi-day tests. So we did something slightly different and introduced load and unload, reload to a higher level loading blocks. So we did a series of loading blocks in different ultimate loads at the end of its loading cycle until failure. And periodically we stopped and we were taking measurements with all the sensors. There was not continuous recording, but periodically in specific number of cycles. So actually, let me remind you again the SHM technologies. We have strain sensors via FBGs that are on the FOD panels, an FBG sensor network, as well as printed PCT sensors and conventional PCT sensors that are of higher TRL, and we are more confident that they are working properly. After all, the PCT sensors is a very new, rather low TRL technology. So we wanted to be sure that we have reliable lamp wave measurements. We tested for many weeks, and in the following I will show you how we leveraged the strain data as well as the guided wave data separately at the moment to see what we can achieve in terms of diagnostic and prognostics. And let me show you the pipeline, as we call it, the machine learning pipeline that we developed for the handling of the strain data. So starting from the structure, from the engineering structure, whatever this can be. In our case, it was this FOD panel. It could be a wind turbine blade, or it could be any other type of composite or metallic structure that is properly sensorized. And you see here the strain, the FBG sensor, the fiber optic cable. Periodically throughout the tests, we get the raw strains. We developed here a health indicator that we wanted actually to be insensitive to the load changes. So we developed a health indicator that is insensitive to the loading, to the load unload reloading sequences, and captures only changes due to damage and damage propagation. So we developed a health indicator based on differentiating actually the raw strain measurements. And we used these health indicators as an input to an actually rather new evolution in the machine learning field, which is called the graph neural nets. And the reason why I used graph neural nets is because it's a very appropriate architecture to take into advantage knowledge between different sensors, interconnection, interconnectivity, connectivity between different sensors. So it's an architecture that leverages this kind of stuff. It's used in totally different applications like mining from social networks, data and stuff like this. It's a quite new development. And we use this to build two different networks. One for diagnostics. By diagnostics here, we mean the stiffness assessment. We wanted to see how stiffness is degrading throughout the test. And the prognostic task, which is the remaining useful life estimation. And by remaining useful life, you have to assign an end of life to your structure. We did this, again, in close communication with SAFRAN. In terms of stiffness reduction, we have 1% stiffness reduction as an end of life, 5%, 10%, 15% stiffness reduction. And the results, you can see here, you can evaluate on yourself the result here. With the blue line, it's the true stiffness reduction. Before elaborating on this, let me tell you that we have 5 panels, and to train the machine learning algorithms, every time in a cross-validation approach, we leave one out. So the test set is unseen throughout the training, and this has to be always taken care of. With the blue line, you see the true stiffness reduction throughout the test, normalized. And with the red line, together with the confidence interval behind the prediction, you can see what is the estimation of the machine learning algorithm. It was quite good for us. The mean absolute percentage error is around 2% in most cases, which is very good and very interesting. Actually better than we expected, to be honest. And in terms of the prognostic results, the remaining useful life in 1%, 5%, 10%, and 15% is again quite good. The red line is very close to the blue line, which is the ground truth. But the mean absolute percentage error is around 15% or so, which is still much better than what we have seen in previous projects. We have been investigating these approaches, diagnostic and prognostic approaches, for about the last 10 years. And it was probably the first time that we see these technologies to be mature enough, or we are mature enough, I don't know, to bring such good performance metrics. Of course, it's always dependent on the training data and the application. In the end, as people from the machine learning community say, it's not the one who has the better or the fanciest algorithms that wins the game. It's the one that has the most representative training data in the end. So this is a message to the community that if we want to leverage this intelligent machine learning stuff, we have to have good, representative, accurate, validated training data. Okay. We checked also what we could achieve with simpler architectures, like MLPs, simpler neural networks. And it was clear that the GNN, the graph neural network architecture, can on average score much better than simple LSPs. The reason that we think this happens is that, as we say here, GNNs are capable of capturing cross-sensor relations. So it's an ideal architecture when you have sensor networks and sensorized structures, especially for strain sensors, which are affected very locally by damage. And sensors that are far from the damage field are not as much affected by those the strain perturbations induced by damage. Okay, the same for prognostics. Let me pass this through. This is the prognostic result for 1% stiffness drop, which was actually the best because it's easier to capture the performance before stiffness drops very rapidly towards the end of life. It's getting more difficult for the algorithm to understand this. But still, even in higher end of lives, you can see our estimates being being quite close to the ground truth, to the blue line. So again, the red line is the estimate, the outcome of the machine learning algorithm, and the blue line is what we call the ground truth. And the confidence interval says, well, interestingly enough, you can see that the uncertainty is narrowing, is closing, as we come towards the end, and you have more data and your algorithm is more confident to the result that it gives you. This is also a good indication when you see the uncertainty decreasing towards the end. Let me go to the next let's say approach, where we want to leverage, to utilize guided waves data to perform the same task, diagnostic and prognostic. I will show you the prognostic part. The diagnostic part has finished later, a little bit later than that, but it's in principle the same. The pipeline is similar. Out of a sensorized structure with the PZT sensors, we used only the conventional PZT sensors here, not the printed PZTs, as they are actually still under assessment. So we relied on the conventional PZTs. We extracted the raw data, and an innovation that we used in this work is that we did not perform any manual feature extraction out of the guided waves. We inserted a big part of them, truncated in about 500 microseconds to capture the first part, you know, the EA0 or the S0 part of the guided wave, as inputs to another fancy architecture, another fancy deep convolutional network that it's called Inception CNN. And it's called Inception from the movie, from the well-known movie, because it has different layers of different kernels and different features, which is very interesting in our case because it performs what we call a hierarchical feature extraction. From the raw signal, we let the algorithm choose on its own as to which features he has to associate with the output, which is the remaining useful life. Here is the remaining useful life estimate. Just to show you the size of the data in several points periodically throughout the test. You can see here the test in terms of stiffness reduced until the end of life, until the total collapse of the panel. The conventional PZT sensors, one every time in circular manner, one is used as an actuator and the other three as receivers. For various diagnostic frequencies, starting from 50 kilohertz, 100, 150, 200, and 250 kilohertz. And at each point, we have 4 repetitions with each sensor acting at least once as an actuator. And 10 repetitions for each time. Total signals for each point, 200 for each periodic moment that you get measurements. We averaged to counteract with some signal stochasticity that we observed here. we use time synchronous averaging. And we also tried, we did not only try the inception CNNs, but we tried a plethora of machine learning algorithms like transformers or Hilbert feature CNN or NestNet CNN or even a simple multi-layer perceptron, a simple MLP. And in most cases, and for sure on average, the inception CNN worked and scored much better in terms of root mean square error. The performance, if we keep this as performance metric, but for any other performance metric, the performance of the inception CNN was much better than its competitors, let's say. And the reason we believe this happens is what I mentioned before, this hierarchical approach to the feature extraction that this architecture allows. These are the results, the prognostic results for the best case. In the we had also not such very nice results, and it's very interesting for us to compare it with what we obtained from strains. And actually, strains performed better, strain-based algorithm. You know, we are still discussing with the colleagues why this is happening. Another approach also is to see what happens if we fuse. And I'm looking at Morteza because this was his PhD. If we fuse both techniques to see what if we can obtain better results than each one on its own. You see, how is my time? Okay, so this means I'm already late. So let me pass you through quickly, sorry. We also assessed which frequency scored better, and we saw that on average the lowest one scores better, maybe due to lesser attenuation. And let me guide you through the conclusions. Okay, we saw very good performance in stiffness reduction in the strain-based results, in stiffness reduction and rule estimation, very good uncertainty, narrowing uncertainty. Let me pass those quickly through. I want to stay in performance. I don't have. Let me just stress the importance, as I said that before, the importance of training and training data. If you have good training data, you have good algorithms, and you can do these things that in the beginning of the project they seemed too ambitious, you can actually achieve and deliver. So what Morpho gave us was an excellent opportunity to perform these very elaborate and expensive tests and see that these concepts can work. They have the capability to work. So I will talk more later on the SHM roundtable this afternoon, where we will have the chance to exchange ideas. Thank you very much for your attention.
Thanks.
Yes, Elena?
So, does the graph neural network help with explainability, like understanding which type of net neuron is doing what, or if you can spot something wrong, or maybe apply the generalize to similar designs?
That's a very good question. Again, explainability is important, but still, GNN is not a glass box approach. It's still a black box approach. But it can offer you insights on which sensors, which nodes are better related with the others to give you the optimal performance and the optimal outcome. But it's still a black box approach.
No, there is a damage index in the first work with the strain.
The health indicator.
There is a health indicator. It's not raw data. For the PZT, it's raw data.
Correct. But again, explainability, and by explainability, I mean to understand why the algorithm gave and how it gave this result. We still have some roads to go to.
Questions? Yes.
Yes, Theo. You processed separately FPG data.
Yes. Yes. Two different routes.
Could you imagine that we can take benefits of both?
This is what I said on fusion.
Yes.
There are approaches to fuse either on raw depth indicator level or in this.
This life cycle, it's and disassembly, because here we have from the experimental and Quentin from Comet in Belgium. Okay. The floor is yours.
Okay.
Thank you.
Thank you, Nazih, for the kind introduction. I would like also from my side to welcome you and to thank you for being here. It is a pleasure and honor to present you the results from the participation in the project. In this work package, we have worked together with PIM Laboratory in Paris, and under the coordination of Laurent Bert, who is an expert on laser shock. So we had the chance to test the method for the disassembly of hybrid structures, and by hybrid I mean metallic composite structures. So before going to the recycling task, which will be presented to you by Quentin, I will show you our results on the implementation of laser shock technology for the disassembly of the FOD panel. The main objective was to debond the metallic protective layer, which is placed at the leading edge of the FOD, from the composite core. And to do this, we have used the laser shock technology, which is based on the shock wave, which is guided and propagated within the material, and it is caused by plasma on the surface of the specimen. I'm sorry. And you can see here two pictures describing the main idea, describing the concept and how the waves are propagating inside the material. And from the interaction of the waves, we create tensile stress fields at specific points of the material. And these tensile stress fields are causing debonding, interfacial fracture. So the objectives were to develop the method and test the method as a disassembly method. Of course, initially we tried to experimentally demonstrate the method. And also at the same time, we have developed a numerical model which was used to virtually optimize the method by tuning the parameters of the laser. And at the end, we have used the model to upscale the process at the FOD panel, because due to limitations of the number of panels that were available in the project, we couldn't perform laser shock tests on the panel. So this process has been performed entirely numerically. This is a description of the methodology. We developed the model at coupon level, we validate the model, then we have performed some tests at coupon level in order to test the process, and then we developed the model of the FOD panel, and we have managed to demonstrate the applicability of the method at a large scale. So for the at coupon level, we have developed a small FE model, which is comprised of the metallic layer, which initially was made from titanium, then it was changed to stainless steel, And this metallic layer is adhesively bonded to the composite core. And by performing laser shock simulations, the spot was here at the middle. We, let's say, investigated and optimized the process in order to break the interface between the top layer and the composite skin, and to finally achieve debonding. So, of course, in the model, we don't simulate the laser. We don't simulate the process of creating the pulse, but we just apply a pressure profile that is computed from the laser simulation, and we apply this pressure profile on the top surface of the model using a circular spot. And here you can see how the pressure profile is distributed in the circular spot. So for the model, this is a dynamic simulation, a shock wave propagation simulation, which is caused by this pressure profile. So the composite skin was made of a complicated 3D woven material, and in order to obtain the detailed properties that we need for the simulation, we have performed a multi-scale simulation in which we developed a detailed FE model of the 3D woven material at the micro level, as you can see here, and we have loaded this RVE, this representative volume element, in order to obtain the different mechanical properties of the composite material, elastic properties and strengths as well. And also, the purpose of this modeling approach was to go afterwards to a homogenized FE model, because we couldn't use, of course, this detailed FE model in the specimen and the FOD, but we used a homogenized FE model, which is shown here. And in this homogenized FE model, we have, let's say, we have considered the properties that we have computed at this level using the detailed FE model. So these are the two specimens which were used at the coupon level for simulating debonding due to laser shock. You can see here a few details of the model. We have consider the material model of Johnson, Cook, and Gruneisen for the titanium. We have used cohesive modeling, cohesive elements to model the bond line and simulate the bonding. And for the composite, we have used MAT162, which is a material model that considers progressive damage modeling in the LS Dyna, in order to be able at the same time to compute damage in the composite core, because we wanted to see that during the laser shock process, if the composite material is damaged. In this video, you can see how the laser shock causes the wave that propagates in the specimen. We have, of course, the development of release waves as well. And the interaction of the release wave with the primary wave is causing the tensile stress field that leads to debonding. Okay, so at coupon level, we performed also tests, as mentioned before, and we have detected debonding using microscopy. You can see here the area where the adhesive, which is this green this yellow layer, this is the titanium layer. Here is the area of debonding and how this area propagates. You can see here the measurement of this area. And we have compared these experimental measurements with the numerically predicted debonding in terms of debonding length. And we have managed to achieve a very good correlation between the model and the test. And this was a very good validation of the model, and this gives us also the ignition to proceed to the model of the FOD panel. For the FOD panel, things are more complicated because we want to fully debond the metallic protective layer, which is curved at the leading edge. This means that we need to debond first the upper surface and then the lower surface. And in order to do this, we have developed a process in Python in order to apply consecutive laser shocks. And also we have tested the symmetric laser shock configuration, which was proved more efficient. So before proceeding to the debonding simulation at the FOD panel, we performed, let's say, a parametric study in order to optimize the process and to be able to apply repeated shocks at different points of the FOD. You can see here a part of the FOD panel, and also you can see here the repeated shocks, which was at different locations. These circles correspond to the laser's circular spot. So as I told you, we have decided, we have concluded that the symmetric laser shock configuration is more efficient in order to be able to fully debond the metallic protective layer. And here you can see the results from load 1 to load 29. So we have 29 laser shocks. And you can see here how damage is created with the colors moving from blue to red. And also you can see from load 1 to load 29 the eroded, deleted elements, which correspond to the fully debonded, let's say, areas. So we have managed to fully debond the metallic protective layer, except from the leading edge, the nose here, which was very difficult to debond. At the same time, we have checked for damage in the composite core, and we have seen that we have matrix cracking. Here you can see with the blue color matrix cracking perpendicular to fibers and parallel to fibers, but we didn't have fiber damage. We didn't have fiber fracture, so this is a very good indication for the recycling process that using the laser shock disassembly method, we can have, let's say, a separation of the two materials, and then we can proceed with the composite part to the recycling process in order to recover the fibers which are intact after this disassembly process. So the conclusions are that we have managed to demonstrate experimentally that the method is efficient, can be used as a disassembly method, and also we have developed a numerical model which has been validated and used at coupon level to optimize the process, and then this model has been used to upscale, to scale up the process to a structural part. So the experimental process and the numerical model combined can be, let's say, used to an optimized implementation of the process for the disassembly of structural part. At this point, I would like to thank my colleague Laurent Bert from PIM for inviting us to the project, for giving us the chance to work together, and also, of course, to thank him for conducting the experiments. And also, thank you for your attention.
Oh no. Okay. Then when the titanium layer has been removed, we are left with the CFRP, which is a carbon fiber reinforced polymer. And we must find a solution for the recycling of this material. Maybe first of all, I wanted to give you a short introduction about Comet. In few words, Comet is a metal, is a Belgian metal recycling family-owned company. We have 2 trading sites located in Belgium. We recycle approximately 1 million tons per year of metal waste. We generate in turn a lot of what we call shredder residue. And we develop internally all the technologies with our R&D department that will be used to process what we call the shredder residue, in which we will find the non-ferrous metals, the plastics. We will have also mineral fractions, so that at the end, today we are certified to to recycle at more than 95% end-of-life vehicles. But end-of-life vehicles is not the only input in our process. We have here example of what we can have. We have electrical scooters, as well our electronic devices, or collecting scraps. And today the purpose is to find a solution for the carbon fiber recycling. We identified that the most promising process in terms of for industrial application is the recycling by pyrolysis followed by an oxidation process, which is quite good because we have built in our plant semi-industrial pilot demonstration facility for the pyrolysis of end-of-life shredder residue organic. And the purpose of the project was to see how this process could be also applied for the recovery of carbon fiber. On paper, this is quite easy to recycle carbon fiber. First of all, you need to pyrolyze the material at a temperature of approximately 500 degrees, which consists in heating the material without oxygen. And in that condition, the resin, which is around the carbon fiber, will be destroyed. And then you have to oxidize the solid residue that you get after the pyrolysis to clean the fiber from the small particle of solid residue that still contaminates the carbon fiber. To make the assessments at the pilot scale, we had first to find the optimal operating parameters that could be upscaled into our plant, and that's why the first part of the research was to make a lot of tests at a small scale, and then to analyze the properties of the mechanic of the carbon fiber we recover, and then to upscale it into our plant. Of course, it was an iterative process. This is all the experimental setup that were used. On the left, you have all the lab scale equipment, from the smallest to the largest one. And then here, this is an illustration of the pyrolysis plant that we have for the final test. This pyrolysis plant has a pyrolyzer of 400 liters of volumes, so it will require a large volume of carbon fiber to properly operate. Okay. At smaller scale, at the lab scale test showed that the optimal parameters for the recovery of the carbon fiber was a pyrolysis of 2 hours at 500 degrees, followed by oxidation of 30 minutes at also 500 degrees, which is quite good because our machine is designed to work optimally at 500 degrees, and we do not have the possibility to change so easily the temperature of the reactor between the phases of pyrolysis and oxidation. For production reasons, it's much more easier to work at stable temperature. So the findings at lab scale are very, very good for, let's say, future implementation at a larger scale. And the mechanical properties the degradation of mechanical properties is limited to 10% in that condition. This is a detail of the mechanical properties that have been measured on the recovered carbon fiber. Interesting here on the picture is to see at the microscopic level the effect of the pyrolysis step followed by the oxidation. And in function, as much as you pyrolyze and oxidize, as much as you clean the fiber, but as much also as you degrade the mechanical properties. So you have to find compromise. On the left, the virgin carbon fiber. On the right, the recovered carbon fiber. At semi-industrial scale, we then when we have found the parameters at a smaller scale, then we implemented it at larger scale, and of course it's not that easy, because there is numbers of other parameters that must be taken into account. For example, the geometry of the material has an importance, because of course the large-scale reactor doesn't behave as a small lab equipment reactor. Also, the heat transfer is not the same, and if we want to have, let's say, quite constant quality of recovered carbon fiber, we have also to manage the feedstock in terms of granulometry. So it is not possible at that stage to parallelize, to recycle full, for example, FOD panel, because the exposure to the heat of every particle of the material won't be the same, and then at the end you will have also some differences in terms of the mechanical properties of the recovered carbon fiber we can get. So you have to go through a step of shredding to reduce the size of the carbon fiber. Here, this is typically chopped carbon fiber, so shredded carbon fiber, and in that condition you can have homogeneous homogeneity in the processing of the carbon fiber, and then also in the mechanical properties. Nevertheless, you will lose the length of the carbon fiber, and so the application for the recovered carbon fiber is not the same than for the virgin carbon fiber. But we demonstrated that our machine is well adapted to chopped carbon fiber, which is interesting and opens the perspective for, let's say, industrial applications. And here we did an economical assessment based on all the data we have collected throughout the project. And this is quite optimistic, because we have measured that the process can be energetically self-sufficient. It means that no other source of heat is necessary than the energy contained in the pyrolyzed material to heat up the process. Nevertheless, you will need to add some electricity to run the motor of the plant. This is one finding. The other finding is that to have a process which is economically viable, we would need to pyrolyze at least approximately 1,000 tons per year of carbon fiber. And today, yes, I will go to that to the next slide. First of all, I wanted to speak about the recarbon fiber market price, which is quite interesting to note that the carbon fibers is of course the valuable material into the CFRP, and thanks to the high value of the virgin carbon fiber, recovered carbon fiber can also be of quite high value. Here, for example, 60% is the 60% of the virgin carbon fiber. 60% of the price of the virgin carbon fiber is usually the price which is announced by the market for recycled product. And here, even with the lowest grade virgin carbon fiber, we stay at approximately 6,000 euro per ton, which is very high, interesting price for this kind of material. And also in terms of capacity, I wanted just to say that today, for example, the aviation and aerospace sector, including the defense, produce approximately 6,000 in Europe, 6,000 tons per year of waste. So if you want today to make a plant for 1,000 tons per year of waste, I think it will be difficult, because we have also to guarantee the supply of this material and to supply the material of good quality, which is not too much contaminated by I don't know what, but other product than carbon fiber. But in the coming years, this is obvious that it will become more and more interesting, because the production of wasted carbon fiber will explode, as the figures here shows. So this is very interesting to note that we are quite confident with the technology we already have. We will be able in the next years to go on this market. And so, to finish the conclusion of our common work, of course, all the previous work that has been done by our colleagues will help to increase the lifetime of the product, but everything, of course, comes to an end. And it is important first to remove all the valuable part of the carbon fiber before going into the final process for the recovery, and the schema here shows that.
Thank you. Is there any questions? Questions? Remark?
Yes, yes, please.
Thanks for your presentation. Rather than shop fibers, is it possible to recover or maintain the original structure of the carbon fiber?
We tried, but imagine as large is your piece, as long as the time of the external fiber will be exposed compared to the internal fiber, and so the condition of the heat transfer won't be the same for the inner fiber than the external fibers. So from an industrial perspective, this is much more reliable and efficient to go first to first shred and then to
and the idea is that the recycled will not going to be used in aeronautical for some surgical part, but perhaps for automotive, for something that is not very structural. So then you can reuse it in another industry, not for sensitive or structures.
On the table there,
yes,
there is
you have some
there is an example of that. You have the shredded material, and you have the FOD panel as such. And you will immediately see what is wrong.
Okay, so you are invited to see the example. So thank you very much. We have 15 minutes left, but it's okay, delay. So thank you very much, and thank you all. We will have a break, and then we will go through the, yes?
Yes, we are. She said you have to take some pictures behind.
I don't know how to remove.
With some Morpho stuff.